So good morning, I'm Jo Evershed, and as David said, I'm the director of IndexMatch, a company which specializes in teaching financial modeling and decision analysis using Excel. Now, our clients come to us for this service because it bridges some of the gap between school maths education and what's needed in industry, and particularly what's needed in the city. And they use us because we've built a platform that's based on evidence from the cognitive sciences. So today I'm going to speak about two things, both industry needs, which I expect there's quite a lot of consensus in the room, and we're going to hear more about it. So I'm going to also shift the focus over to what solutions there are and how they're supported by scientific evidence. Because if there's one point I'm really critical on that I really want you to take away today, is that whatever solutions we come up with, if they're supported by evidence from the cognitive sciences, they're going to be much easier to get out through society, because it's going to be harder to critique them and say, no, they won't work. If you've got the evidence base, you've got a much stronger message. So you may be wondering what financial modeling and decision analysis is, and you wouldn't be the only person. I spend a lot of my time explaining. So this is Excel. You may not have seen Excel looking like this before. You may have. This is a financial model. This is one of our teaching financial models that we use to get people to practice building a financial model. What you've got here is you'll see a set of inputs on the front panel. You've got a cash flow, which is the graph, and then you've got some key outputs. And what you're creating when you build a financial model is a decision tool. You're putting a tool to a management panel who might not be mathematically literate, and you're trying to help them make evidence-based decisions, the best decision they can make under uncertainty. So you've created a model for them which allows them to play with the inputs and see the impact on key decision metrics at the output. So critically, this is a model you're using to communicate with people who might not be maths literate. If you do not have the communication skills as a mathematician to communicate with somebody who is not maths literate, you are not yet useful enough. So you can change the inputs. If you pay attention to the red bars on the graph, you'll see how revenue changes. So at the moment, we're looking at a tolling model. If we change the business strategy to a merchant model, you can see you make less money in this particular instance. But if we change the commodity price, you'll see, wow, our revenue goes up. Isn't that great? And you can also see the tax impact. Maybe you want to change another parameter. What's that? We've changed the economies of scale here. We're going from a small investment to a really large investment. And you see you make much more money. And finally, we might play with whether you've got financing or not. So if you watch at the beginning where you're making your CapEx investment, how much finance are you managing to pull in? All the green bars disappear, and that changes your rate of return. So this is how you can use Excel to create a mathematical model, a financial model. Now, recruiting people to do this job is really hard. I used to interview about 50 to 100 people to find one candidate who I thought was worthwhile taking on and training up to be a financial modeler. And what we tend to use in our interviews, and this seems to be used across the whole financial modeling and decision analysis industry, is estimation problems. Because estimation problems are really powerful at seeing whether somebody can think through and create a model in their head, use knowledge they have of the world, and then come to an answer that they think is valid and defendable and can inform a decision. So, what's an example of an estimation problem? This is a typical interview question. How many maternity beds are there in the UK? Now, you should be able to do this in your head using pre-GCSE level maths. And yet the candidates that we interview, who have maths degrees, physics degrees, chemistry degrees, economics degrees, they can't do this. It's a really simple question, but they can't do it. We've had answers as high as 4 million and as low as 400, and you'd hope those wouldn't even pass a sanity test. So, in case you're all sitting there going, I can't listen because I need to work out how this is because I'm a mathematician and I need the answer. Here you go. I know you could all work it out in time. We just don't have the time. You can get within 10% of the actual answer just using the numbers in your head. You need to know the population of the UK, and you need to derive the birth rate, which, as long as you know that women have children and how many children they have on average and how long they're fertile for, you can get to, and you should have that. You need to know how many days there are in a year and the length of stay in hospital. And you might want to apply a contingency because you might understand that if government gets this wrong, it's really, really bad frontline news. So this is a question that we would ask. And as I said, many people get it wrong. So at some level, this must mean that our mathematical education system is not developing skills that are essential for even quite simple mathematical reasoning, let alone complex mathematical reason. So let's go back and have a look at the core skills of mathematical reasoning. As you can see, it turns out that mathematical reasoning takes a mixture of analytical research and communication skills, and you may also notice that the ability to do mental arithmetic isn't on the list. As you've seen, we use machines to do the calculations for us. So a key question for today is how can we restructure the maths curriculum to develop mathematical reasoning skills? Now, what you do see here is that this communication element, structuring the question, researching and communicating, are core skills. And these are skills that are more traditionally associated with the humanities. So let's have a look at how we teach the humanities. When we learn English, we don't just do basic letter and word recognition or basic grammar and punctuation. We read books, we read poems, we study great literature and great journalism. We examine the ways that language is used both practically and artistically. We teach it in a manner that is applied. And we get people to give it a go. We get them to write so that they practice the skills that they're going to need. We get them to write essays and write stories. But importantly, I think it's this exposure to the value of language that inspires them to persevere with these basic reading and writing skills and become skilled while they're still at school. And this is how we teach maths, at least historically this is how we teach maths. And, you know, no wonder people say it doesn't seem important or has no space for creativity. And it's really exciting to be here with a group of people who want to change this, because I think we can really take this forward and go far. The important thing is that there are complex, interesting, and exciting mathematical questions that are relevant to students' lives that they can engage with while they're still at school. And interestingly, exploring these questions not only teaches mathematics, but can also shape thinking about important social problems and develop essential life skills. For instance, whether going to university is worth the financial and time investment. That's a really interesting question to school leavers. Should I go? Should I spend the money? Should I take the time? Similarly, what is the comparative acreage required to heat and fuel all the schools in the country using wind versus solar? There's a lot of debate in the press about the merits of different renewable energy systems, but answering that question involves needing to use mathematics to shape your answer and understanding the trade-offs. So you get people involved in these interesting questions that have social relevance. You really change the level of debate out there in the real world. And perhaps my particular favourite, whether they should ever borrow money from Wonga.com. And if we get to a point where no one in the country borrows from Wonga.com, I think we would have done a good job. Taking an applied approach does not mean that the mathematics is being dumbed down. The engaging and relevant examples shown before can require some quite serious mathematics, as you can see here. Quite a few of these you'll recognise as part of the GCSE and A-level curriculum. People readily accept that teaching applied mathematics would be more fun and engaging, but there is great concern that taking this approach will fail to develop an abstract understanding of mathematics and abstract mathematical reasoning facilities. I think Conrad brought this up earlier. People go, no, but they're not really going to know maths. If they've done it in applied fashion, they're not going to get maths. And I think this is a really valid concern that needs to be addressed. Now, this concern rests on an assumption about the formation of abstract representations. So, as I'm a brain scientist, I think it's appropriate to have a closer look at what empirical evidence has shown us about this formation of abstract representations and use this to inform the decision about how to best develop the maths curriculum. Now, we don't have a lot of time to go into the details about cognition and the representation of abstract meaning. So what follows is a couple of big ideas that are particularly relevant to this discussion. Our current understanding, and I'm a scientist, so we need to know this with a degree of certainty that we feel is acceptable in the science community, but of course it's not definitely true, and models will change over time. Our current understanding is that in order to form abstract representations that are context-independent and therefore usable in original thought, you have to have multiple contextually different experiences. Now, what does this mean? Here is a non-maths example. What is the common element in the three pictures shown here? The skin protects the body from infection, your clothes protect the body from the cold, and your house provides protection against the weather. Providing these multiply contextually different experiences, the structural element that is in common, in this case the idea of a protective barrier, or in more abstract terms, a delineating boundary, is naturally isolated. And additionally, this isolated representation retains its links back to the context in which it was created. And this is really important because when you have an abstract representation that is formed out of a perceptually concrete domain, when you come across that perceptual trigger again, when you see that in real life, your abstract representation will be automatically triggered. To go back to somebody's point about not needing any brain, or somebody had said they didn't need any information in their head, they could look it up. But you need to know what to look up. Your brain needs to know when it sees it in the real world what abstract representation it's linked back to. And similarly, if you only teach in an abstract way, you don't form these links back. So there is no trigger to say, yes, here I need to use Pythagoras because I'm dealing with whatever it is. So what we learn from brain science here is that by teaching using practical experience first and covering the theory second, you actually form stronger and not weaker abstract representations. Now, the second point that's important to cover is once you form the abstract representation by having these multiple concrete experiences, it is useful to go over the theory as well. That creates another strengthening loop on what the theory is and allows them to link back to the perceptual cues. So to return to the concern that teaching applied maths will result in poorer abstract mathematical reasoning, we now see that this idea is flawed because it doesn't take account of how abstract representations are formed. Crucially, abstract representations are not created by describing a context-free idea. For instance, the idea of a barrier between two spaces. It's very tempting to just teach the abstracted version, because once you've got it, that's what you use all the time, and it feels far more efficient to just teach that. But that's just not the way the brain works. So, putting these two arguments together, maths is more interesting and more obviously relevant subject when it's used to engage with interesting problems, and teaching in an applied context first and covering the theory second results in better and more transferable abstract representations. It naturally follows that future maths education should have a maths equivalent to the literature component of English, in which students develop their mathematical reasoning and communication skills. In this so-called, I'm going to call it literature component, students would use standard industry tools to engage in modeling and analyzing real-world data sets to derive arguments and answers based on their analysis. So here's an example. This is an example I came up with. So it hasn't been under a lot of scrutiny, but it will give you a flavor. This is roller coaster trouble. Customers are complaining that the Thriller roller coaster is too scary. A senior engineer at Six Flags Astroworld, Texas, please advise what changes should be made and why. Now, the reason I've picked this example is that the technical specifications of a whole load of real-world roller coasters are available online. How cool is that? You can download the roller coasters at Thorpe Park and look at how they've been designed. Now, once you've got the technical specifications, you can build your model. And this is a great opportunity to think about Jolt. So Jolt is what you optimize in when you're building a roller coaster to create that sicky, horrible, awful feeling that I can't stand. But what Jolt is the third derivative of position. So you build your model of this real-world roller coaster that you've been on, you identify the scariest bit in this ride, and then you need to make write a report back to your senior management at Flags Astroworld and advise in English what they should change and why. And so now you're developing not only your mathematical reasoning skills, but also your mathematical communication skills. And I believe that these types of applied classes would better prepare students for university and for industry and for life in general. So to summarize, we propose a maths equivalent to the English literature curriculum because, firstly, it ensures that the point of mathematics is kept central in the curriculum. Secondly, it develops students' capacity to use mathematics to answer real-world questions. Thirdly, it ensures that the abstract mathematical representations are appropriately linked to contextual cues. And remember, it's this which is essential for knowledge transfer, which is what's really important for novel thought. And finally, it ensures that they develop the broader skills needed for the communication of mathematical reasoning, rather than just the ability to perform the mathematical calculation.